Okay, hi folks, welcome back to another National 5 Physics past paper walkthrough, and this time, hot on the heels of the publication of the 2025 paper, we're going to have a look at the multiple choice section. Now, all these papers are available, of course, on the SQA website, but they're also available on my school website. It's called the Glen High School Physics page. I'm going to click on the National 5 page, scroll down to N5 SQA past papers, and it's the first one in the table there. Now, I've called it paper 1. I should really call it section 1 because it's a single paper. There it's there, 2025 National 5 Physics paper. It's 2.5 hours. And so the multiple choice part, section 1, should take you about 45 minutes. I'm going to try and do it in about half an hour. So might be a kind of speedy walkthrough here. First thing you see is the data sheet. You're not really going to need that much in this paper. I think the only time is you're going to need the gravitational field strength of Mars in one of the questions. But we'll see how we go. Anyway, as usual, make sure you have a look at the questions first, then come back once you're ready and you'll see how we have done it. So let's go then. And remember to pause if you're doing the question first. This is question 1. Which row in the table shows both quantities classified correctly? Well, the headings in the table are scalar and vector. Well, there are 5 quantities in National 5 Physics that are vector quantities, and they are displacement, velocity, acceleration, force, and weight. And by vector, we mean that they need a direction for those quantities to be fully described. So if we look at the right-hand column of the table that's headed vector, then the only ones that are present are force and velocity. All the other ones there, distance, mass and time, are scalars. And remember, a scalar is a quantity that can be fully described by its magnitude only. So scalars don't need a direction. And if we look at the scalars column, then weight, force and velocity are vectors, so they are not correctly classified, so it's only distance and mass there that are correct. So the only row that's correct is row B. So question 1, answer B. Question 2, the graph shows how the velocity of an object varies with time, and we have to work out the displacement of the object at 2 seconds. Well, notice the graph is a velocity that's, well, it's decreasing, and at a time of 1.5 seconds, the velocity decreases to 0 and the object changes direction, because the velocity is then increasing negatively. So if we want to work out the displacement, we need to work out the area under the graph of area 1 and also the area under the graph of area 2, but we're going to subtract 2 from 1. So if we work out the first area, remember the area of a triangle is a half the base times the height. So in this case that's going to be a half of 1.5 times 6, and that gives us an answer of 4.5 metres. And then we work out the area under the graph for area 2, which again is a triangle. So we do a half the base times the height. In this case the base of the yellow triangle is 0.5, so it's a half times 0.5, and the height in this case is negative 2 because it's going in the opposite direction. Remember, velocity is a vector. And if you do that, careful in the calculator here, it's a half times minus 2, that gives us negative 0.5 metres. So the total displacement then, if we add the two areas together, is 4.5 plus negative 0.5. That gives us 4 metres. That means question 2 is answer A. Question 3. A car is travelling along a straight level road. The car slows down at a constant rate of 2 metres per second squared for a time of 8 seconds, and the final speed is 5 metres per second. And we have to work out the initial speed of the car. So let's make our little shopping list, U, V, A and T, and fill in what we know. So the initial speed is what we're looking for, so we'll put a question mark there. Final speed was 5 metres per second. The acceleration is negative 2 because it's slowing down at a constant rate of 2 metres per second squared. And the time was 8 seconds. And then we go to our relationship sheet and select an appropriate relationship here for this calculation. It's going to be A equals V minus U over T. It's U that we are looking for. So let's sub everything in first. So A was minus 2, so it's going to be minus 2 is equal to 5 minus U over 8 seconds. Then we multiply both sides by 8. We'll get minus 16 equals 5 minus U. So that means that U must be equal to 21 meters per second. And that corresponds to answer D. That's 3D. You could also work that out by realising that if the car loses 2 meters per second every second for 8 seconds, then the car is going to lose 16 meters per second. And if it ends up with a final speed of 5 meters per second, then it must have started at 21 meters per second. That's question 3. Okay, question 4. A cup rests on a table that rests on the earth. The cup exerts a downward force on the table. Be careful with the words here. Cup, downward force on the table. So the reaction to this force is just the opposite of that. It will be the table exerting an upwards force on the cup. Nothing to do with the earth here. The forces between the two objects. So 4A. Question 5. A crate of mass 180 kilograms is lifted through a height of 3 meters in 2.5 seconds. What's the minimum work done in lifting the crate through this height? Well, we've got a relationship for work done. It's EW equals F times D. And the force that we need to use in this relationship will be the weight of the object. And the distance we lift it through is the height that it moves through. And if you look closely, that's the same relationship as the gain in potential energy, gravitational potential energy, EP equals mgh. So if we sub in all the numbers we know, the mass was 180, g is 9.8 and the height was 3 meters. And that gives us an answer of 5292 joules. Now you've got to watch your rounding here, so that rounds to 5,300 joules, and that corresponds to answer E. That's question 5E. Moving on, question 6. An asteroid of mass 25 kilograms is travelling at a speed of 9,200 meters per second, and on entering the Earth's atmosphere, the asteroid burns up completely, and we have to work out the maximum amount of heat energy released. Well, it's originally got kinetic energy, so we can work that out from EK is a half mv squared. That's a half times 25 times 9,200 squared. That gives us 1.1 times 10 to the 9 joules, and all of that kinetic energy will be changed into heat energy as it burns up in the atmosphere. So the heat energy released will be the same as that. It's 1.1 times 10 to the 9 joules. That corresponds to answer D, 6D. Question 7. The speed of a satellite in orbit around the Earth is given by a relationship you've never seen before. It's V equals the square root of R times G, where R is the total distance from the centre of the Earth to the satellite, and G is the gravitational field strength at the location of the satellite. And then we're told the radius of the Earth and the height of the satellite above the surface of the Earth. So we're going to have to add these two distances together to get the total distance from the centre of the Earth. So 6.4 times 10 to the 6 plus the 3.6 times 10 to the 7. That gives us 4.24 times 10 to the 7. And don't round that, because we then have to do V equals the square root of R times G, which is square root of 4.24 times 10 to the 7 times the gravitational field strength at the location of the satellite. Now don't put 9.8 in there, because that satellite in orbit is at a location where the gravitational field strength is only 0.22 newtons per kilogram. And then if you do that correctly on your calculator, it gives you 3,054, which rounds up to 3,100 meters per second, and that corresponds to answer C. That's question 7C. Very tricky. Okay, moving on. Question 8. The weight of an astronaut on Earth is 710 newtons. What will the weight of the astronaut be on Mars? Well, your weight changes, but your mass stays the same. So we need to work out the mass of this guy. We do that using W equals mg. The weight on Earth was 710. The gravity on Earth is 9.8. So the mass of the astronaut will be 710 divided by 9.8 is 72.45. And don't round that, because we're going to have to do another weight calculation, but this time on Mars. So W equals mg. We're going to use the mass of the guy, which is 72.45, and the gravitational field strength from your data sheet. Remember we said that earlier? Well, that's 3.7, and that gives you an answer of 270 newtons. That's it rounded. That's his weight on Mars, so that corresponds to answer C, 8C. Question 9. Sirius is the brightest star in the night sky, and the distance from Earth to Sirius is 8.6 light years. And we have to convert this distance into meters. So we're going to use distance equals speed times time. Because it's light years, we're using the speed of light. Remember, 1 light year is the distance that light travels in 1 year. So we're going to multiply the speed of light by a time of 8.6 years. So that's 8.6 years times 365.25 days in a year, 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. So a big long calculation. And if you do that correctly on your calculator, it gives you an answer of 8.1 times 10 to the 16 metres. That corresponds to answer E. That's 9E. Okay, moving on. Question 10. Still on space stuff. The line spectrum from a star is shown along with the line spectra of the elements hydrogen, helium, carbon and nitrogen. And we have to figure out the elements that are present in the star. So this is a matching job. You've got to figure out what elements are in the fingerprint or the barcode of the star. So let's just pick each line in the star and try and match it up with a line that's in one of the element spectrums. So that first line could be in helium or nitrogen. The second line's, that looks like helium and carbon. Then the next little section, those two lines. A ruler often helps you. If you put a ruler on your paper, it's a bit easier to see which of the lines match up. So helium and carbon seem to be the ones that are present here. I'm going to get rid of that nitrogen line because the nitrogen's definitely not matching up. But if we keep going with helium and carbon, then they are all matching up. Those two thick lines match up. And then those last 3 lines in the star spectrum match with the 3 lines in carbon and helium spectrum. So I think that's it. So the nitrogen doesn't match up, the hydrogen doesn't match up. So that leaves us with helium and carbon. So that's answer question 10C. Moving on then, question 11. Now we're on to electricity. A technician uses an oscilloscope to test 3 different power supplies, and the diagrams represent the traces seen on the screen of an oscilloscope. And you should know that an oscilloscope is a device that displays electrical signals and how they change with respect to time. So a DC supply is constant, so it should be a straight line on an oscilloscope. And an AC supply, as its name suggests, AC is alternating current. It changes direction at regular intervals and it appears as a wave trace on an oscilloscope. So we've got DC, DC and AC. Let's have a look at the answers. So DC, DC, oh no, A is wrong. DC, DC and AC. It can only be answer E. Question 12. An electric field exists around 2 point charges Q and R, and the diagram shows the path taken by a charged particle as it travels through the field, and the motion of the particle is shown. And there we see a little diagram. The path of the particle is being attracted to Q and R. And if it's attracted to Q and R, it must have the opposite charge to particles Q and R. So if the particle's positive, Q and R must be negative. And if you look at the answers, then the first row in the table has got the charge in the particle is positive and Q and R are negative. So that is a possible answer. The only other possible answer would be if the particle was negative and Q and R would have to be positive, but that isn't one of the options. So it can only be question 12, answer A. Question 13, still on electricity. We've got a circuit there with a 12 volt power supply, a series circuit, two resistors sharing that 12 volt supply, and we're told the reading on the voltmeter is 3 volts, and we have to calculate the resistance of resistor R. Well, let's add in another little voltmeter because these two resistors are sharing the 12 volts, and there's 3 volts across the 240 ohm resistor, so there must be 9 volts across resistor R. Now those two voltages are in a ratio of 1 to 3. 9 volts is 3 times bigger than 3 volts, so resistor R must be 3 times bigger than 240 ohms. So it must be 720 ohms, not volts, you double. Just as well my rough working isn't marked in the multiple choice section. Anyway, that's answer D, 13D. Question 14. 3 resistors are connected as shown. They're all 12 ohms, and one 12 ohm resistor is in series with two 12 ohm resistors in parallel. And the wee trick here is that if the resistors are both the same in parallel, then the total is half of one of them. So the total of the two 12 ohm resistors in parallel is 6 ohms. And then all we have to do is add that to the 12 ohm resistor at the top there. So 12 plus 6 is 18 ohms, that's 14D. Question 15. A circuit is set up as shown. It's a series circuit, and the reading on the ammeter is 0.5 amps. So that'll be the current all the way around. And the resistance of the lamp is 8 ohms. So the total resistance of the circuit is 24 ohms. That's why we get a current of half an amp. And we have to work out the power dissipated in the lamp. If you don't like that word dissipated, just ignore it. We have to work out the power in the lamp. So we've got a choice of power equations. We're going to use P equals I squared R because I know what the current is and I know what the resistance of the lamp is. So that gives me 0.5 squared times 8. And if you do that correctly on your calculator, that gives you an answer of 2 watts. And that corresponds to answer A, that's 15A. Question 16. A kettle, a TV and a microwave are connected to the main supply. The kettle's got a power of 2.6 kilowatts, the TV's 170 watts and the microwave is 900 watts. Which row in the table shows the appropriate fuse rating for the kettle, the TV and the microwave? Well, the rule here is if an appliance has got a power more than 700 watts, you use a 13 amp fuse. If it's less than 700 watts, use a 3 amp fuse. So my kettle is 2600 watts, 2.6 kilowatts, so it's got a 13 amp fuse. The TV is less than 700 watts, so it's got a 3 amp fuse. And the microwave, again, it's more than 700 watts, so 13 amp fuse. So we're looking for 13, 3, 13, and it's answer B, 16B. Moving on then, question 17. On to heat energy here. A group of students sets up the experiment shown to determine a value for the specific heat capacity of water. And the students make the following statements about how the experimental procedure could be improved. Statement 1. Insulate the beaker to reduce heat loss to the surroundings. Well, that's always a good idea, so yes. Move the immersion heater further into the water. Well, it's half sticking out of the water, so yes, again, that's a good idea. And statement 3, use a stopwatch to measure the time for which the water was heated. Well, do we need that? Let's have a look at the setup. So there's a joule meter that's measuring the energy supplied, and if we think about the relationship that you would use to work out the specific heat capacity, it's EH equals Cm delta T, and the joule meter is measuring the energy supplied. We also need to know the mass of the water and the change in temperature of the water, so time is not required, so we don't need a stopwatch to measure the time for which the water was heated. So that means it's only statement 1 and statement 2 that's correct. So 1 and 2 only is answer C. Okay, moving on, question 18. A hot substance is cooled, and the graph shows how the temperature of the substance changes with time. And there's two flat regions on this graph as it's cooling. So the first flat region must be when it's changing from a gas to a liquid with no temperature change. And the second flat region must be when it's changing from a liquid to a solid with no temperature change. And then we're told the student makes the following statements about the substance. The boiling point of the substance is 120 degrees C. Well, that is correct, because your boiling point is the point at which you have the liquid to gas state change, when you are either heating it or it's cooling down. So that's correct. Statement 2, at a time of 40 minutes, the substance is a gas. Well, at 40 minutes, it has finished changing from a gas to a liquid, so it will be all liquid. So that's incorrect. Statement 3, the melting point of the substance is 20 degrees C. Well, the graph flattens out at 20 degrees C for the liquid to solid state change. So if we were heating it, when it was a solid, it would change to a liquid at 20 degrees. So 1 and 3 are correct, and that means it's answer C. That's 18C. Okay, moving on, question 19. A ballet dancer wears shoes that have a flat section on the front called a platform. And when the dancer stands on the tips of their toes, the platform on each shoe is flat on the floor. And the area of the platform on each shoe is 1.6 times 10 to the minus 3 meters squared. The weight of the ballet dancer is 520 newtons, and we've to determine the pressure exerted on the floor by the ballet dancer. Well, it's each shoe, so she's got 2 shoes, so we need to double that to get the total area. That'll be 3.2 times 10 to the minus 3 meters squared. And then for the pressure, P equals F over A. F is the weight of the dancer. That's 520 divided by 3.2 times 10 to the minus 3. That gives us our final answer for the pressure of 1.6 times 10 to the 5 pascals. That's answer D, 19D. Moving on then, question 20. A tennis ball contains a fixed mass of air at a temperature of 20 degrees C. This is the gas laws. So remember, as soon as you see temperatures that are in degrees C, you have to change them into Kelvin. So 20 degrees C is 293 Kelvin. Then we're told the initial pressure of the ball, but during a tennis match, the temperature of the air rises to 35 degrees C. That's 308 Kelvin. And then we have to calculate the new pressure of the air inside the ball as it heats up. So the volume remains constant, so we're going to use the relationship that only has pressure and temperature in it. So we're going for P1 over T1 equals P2 over T2. And remember, your temperatures are in Kelvin. So we've got 1.9 times 10 to the 5 divided by 293, and that's going to be equal to P2 over our new temperature of 308. And then we rearrange that to get P2. So P2 is going to be equal to 1.9 times 10 to the 5 times 308 divided by 293. That gives us our answer of 2.00 times 10 to the 5 pascals to 3 significant figures. And that corresponds to answer D. That's 20D. On to the waves questions then. This is question 21. The diagram represents a wave. And which row in the table shows the wavelength and amplitude of the wave? Well, remember, amplitude is the height measured from the middle to a peak or a trough, so we need to half the 0.2 meters, so the amplitude will be 0.1 meters. We've got three options there. And the wavelength, if we count the number of waves that are displayed in the diagram, there's 1, 2, 3. So there's 3 full wavelengths in 120 millimeters. So one wavelength will be 40 millimeters. And then the only row that is correct there is answer B. That's 21B. Question 22. A teacher gives a group of students 2 clues to identify a particular band of the electromagnetic spectrum. And clue 1 says diffracts around obstacles more than visible light. So it must have a longer wavelength than visible light, because longer wavelengths diffract more than shorter wavelengths. And clue 2 says has a greater frequency than microwave radiation. I think we need a little diagram here of the electromagnetic spectrum. So let me sketch one in very quickly. Remember, if we go from right to left there, we're going in the direction of increasing wavelength, and from left to right, we're going in the order of increasing frequency. So longer wavelength than visible light can only be infrared and microwaves, and a greater frequency than microwaves means our only option then is infrared. That corresponds to answer B, 22B. Moving on, question 23. A radioactive source has an average activity of 5.2 megabecquerels over a time of 1.2 hours. And we have to work out the number of nuclear disintegrations or decays that occur in the source in this time. We're going to use the relationship A equals N over T. It's N we're looking for. So let's sub the numbers in that we've got. Activity is 5.2 times 10 to the 6. That's equal to N over a time of 1.2 hours. Now remember to go to convert that into seconds. So 1.2 times 60 times 60. And then if you rearrange that and calculate N, you'll get an answer of 2.2 times 10 to the 10. And that's the number of nuclear disintegrations that you'll get in this time. And that corresponds to answer E, 23E. Question 24. A sample of tissue is exposed to a source of alpha particles, and the equivalent dose received from the source during a time of 5 minutes is 480 microsieverts. And we have to work out the equivalent dose rate. Now all the answers are in microsieverts per second. So let's change the 5 minutes to 300 seconds and then work out how much we're going to get each second then. So we're going to use the relationship H dot is equal to H over T. Now I've actually never used this relationship in my life, but it's on your relationship sheet, so let's use it for clarity. So it's going to be 480 divided by 300. And that gives us our equivalent dose rate of 1.6 microsieverts every second. That's 1.6 microsieverts per second, which corresponds to answer A. That's 24A. Okay, last question then. Energy is released when 2 small nuclei combine during a nuclear reaction to form a larger nucleus. So this is a description of, well, it's nuclear fusion. That's what goes on in the sun with 2 tiny hydrogen nuclei combining to form a helium nucleus. So that's it for the 2025 Section 1 multiple choice questions. And hopefully that will be of some help to some of you. And if it has, don't forget to like, share, subscribe, and we'll see you in the next one. Thanks for watching.